Hello students. So today we are continuing thermal properties of matter. In the last session we have seen different scales to measure temperature and how to convert between various scales. Okay, Celsius to Kelvin, Kelvin to Fahrenheit, then Romer scale. Okay, if we get a faulty thermometer, all those things we have seen. Now today we are going to see the basics of thermometer. Okay, currently we are studying the topic thermometry, that is measurement of temperature. Now the basics of thermometer we will be discussing today, and we will be discussing the reason for expansion. Okay, when we increase the temperature, nothing but by applying heat. So here the main reason for thermal expansion, is mentioned as the asymmetry in the potential energy curve according to atomic asymmetry law. Okay, the reason for thermal expansion is the asymmetry in the potential energy curve. So this R is nothing but the distance between the atoms. Okay, so same behavior is between molecules also. So the distance between the atom or distance between the molecules, if we consider R, its potential energy is, if we plot in y-axis, okay, so its minimum potential energy is at R naught distance. So this side you can see the curve, this side it is asymmetric. So when we increase temperature, that is when we apply heat, okay, okay, or when we increase the temperature, what happens is the distance between the atoms, the distance between the molecules will increase, it will expand, volume will increase, density will decrease. Okay, so this is the reason. Okay, theoretically this is considered as the reason. We must understand this, okay, because these statements are given in our text. Okay, so that is one aspect. Okay, point number one. Okay, so point number one we have seen. Now let us expand this to our temperature volume curve also. So as the temperature increases, when temperature increases, what will happen? Volume will increase. Why volume will increase? Because the distance between the atoms, distance between the molecules will increase, so volume will increase. When the volume increases, what will happen? Density will decrease. Okay, same way when we decrease the temperature, the volume will decrease, density will increase. Okay, so when we draw volume temperature curve, okay, so suppose if we decrease the temperature, this volume will decrease. Okay, so at 100 degree Celsius, okay, suppose a volume of a gas is there, okay, then after some time, okay, it is achievable, but after that we will extrapolate the graph, and this is minus 273.15 degree Celsius, or we can say 0 degree Kelvin. So when it is 0 degree Celsius, it is nothing but 273 degree Kelvin. Okay, 273.15 degree Kelvin. Roughly we can take it as 273 Kelvin. So beyond this temperature, the volume will not be there for the gas. Okay, so practically to some extent only we have done, but if we extrapolate that graph, we will understand that only this much, till this range only temperature can exist. After that the gas itself will not be there, so we can understand that. Okay, so this is called a absolute zero. Okay, in the previous session we have just seen this. Clear? Alright, so when we increase the temperature, okay, volume is decreasing, Okay, when we increase the temperature, volume is increasing. When we decrease the temperature, volume is decreasing. So same way, length, area, or okay, then resistance. If it is a conductor, its resistance also can vary with the temperature. Okay, that we will see. Now, what is the theoretical base for making thermometers? Suppose if we consider this is a bulb. Okay, bulb means the glass tube. You have seen thermometers, right? Same thing. Suppose if this is the thermometer, and if this contains some liquid, okay, maybe liquid. Okay, so example, mercury thermometer is also there. Same way, alcoholic thermometer is also there. Suppose, okay, this much is the level. So what we have seen, when we increase the temperature, what will happen to volume? Volume will increase, obviously. So when we increase the temperature, volume will increase. Suppose if we keep this thermometer in a somewhere around 100 degree Celsius. Okay, suppose, okay, a vessel, okay, this is heat is supplied and this is 100 degree Celsius. This one we have dipped into this. Now after dipping into this, we have taken and we are seeing what will happen to the volume of this liquid. This will rise. Okay, so what we are doing is, we know that upper fixed point and lower fixed point while we study the scale, that we will mark here. Okay, so this is lower fixed point and this is upper fixed point. Say this is 100 degrees Celsius and we will mark here 0 degrees Celsius. Okay, suppose if it is at a room temperature, obviously this will be somewhere here. Okay, maybe 27 degrees Celsius. So that expanding property of this liquid, we are using in order to make the thermometer. Okay, is it clear? Understood or what? Okay, so this is called a calibration. Okay, calibration. If for 1 degree Celsius rise, okay, if the volume is increasing by bit, okay, we will mark there an extra degree Celsius, maybe 10. Then associatively the volume increase, where the next volume will come for 1 degree change, there we will mark 11. Likewise up to 100 we will mark. Okay, this is an example. Okay, this is liquid in glass type of thermometer. Now I will summarize this. Okay, I will summarize this into different type of thermometers. For all of them, what will be the equation that we need to use in order to solve problems? Clear? Okay, now here we have seen an example of liquid. Now, so this can be not only liquid, this can be gas. Gas means it can be at a constant volume, it can be at a constant pressure. Likewise, we can have any type. Okay, so name, okay, the thermometric property. Okay, thermometric property or thermometric quantity. Okay, thermometric quantity means whether it is volume or pressure or resistance, whatever it may be. Okay, then equation. Okay, and we know already, we have seen, suppose how we have done Celsius and other conversions. C by 100 is equal to X. Okay, in any scale. Okay, minus lower fixed point minus divide by upper fixed point minus lower fixed point. This we have done already. Okay, in Celsius conversion. Same pattern will come here also in the equations. Okay, first thing is liquid thermometer. So liquid thermometer. So in liquid thermometer, the volume of the liquid, volume, or even it can be height, volume or height, anything can come. So suppose if it is volume, okay, let us write this is volume, thermometric quantity, volume will be increasing and decreasing. Okay, so here if we need to find the temperature, temperature T is equal to volume at that particular temperature. Okay, volume at that particular temperature, just like this, we do not know, minus volume at 0 degree Celsius divided by volume at 100 degree Celsius minus volume at 0 degree Celsius. Bas over. Okay, so whatever be the thermometric physical quantity we are using, its value at random temperature, its value at lower fixed point, its value at upper fixed point, its value at lower fixed point. If there is a fixed any physical quantity, okay, let it be length, volume or resistance, whatever they give, we can put in this structure and get the equation. So we need not by heart every equation. Okay, this logic can be applied here. Okay, fine. So next one is gas thermometer. So here this can be volume, okay, but if it is volume, then it is at a constant pressure. Whenever we deal with the gas, okay, we need either volume should vary or otherwise pressure should vary. Otherwise, if we don't maintain, okay, either volume or pressure at a constant, okay, if we don't maintain it, one of the physical quantity, okay, as constant, then we won't be able to measure properly. Why? Because, okay, you see PV is equal to nRT. This is called ideal gas equation. Okay, this is called ideal gas equation. So the state of a particle, a state of a gas, that or the condition of a gas, okay, can be communicated or can be conveyed by using three physical quantities, okay, or three variables. What are they? Pressure, volume and temperature. Pressure, volume and temperature. Okay, so this equation, how this equation came, okay, from Boyle's law, Charles' law, okay, all of them putting together only we got this ideal gas equation. Okay, so before coming into this, I shall explain how to deal that also. Okay, okay, so say for example, at a constant temperature, if we maintain the temperature of a gas is constant, then P is inversely proportional to volume. That is, if we maintain constant temperature, then volume, if we increase the volume, okay, pressure will decrease. If we decrease the volume, pressure will increase. Okay, so this was found by a scientist named Boyle. So this is called as Boyle's law. Boyle's law, and this equation is given as PV is equal to what? Constant. Okay, or P1 V1 is equal to P2 V2. Okay, so this is what is Boyle's law. Clear? At a constant temperature. Okay, so this is first law which we used to deal, which we used to study in thermal physics. Okay, note it down. Next one, Okay, next one is at constant volume. At constant volume, P is proportional to T. Okay, if we could maintain the volume of a gas as constant, then how much is the temperature? That much, in that much sense, pressure will increase or decrease. If we increase the temperature, pressure will increase. If we decrease the temperature, pressure will decrease. So this is what is Charles' law. Okay, Charles' law. So P1 by P2 is equal to T1 by T2, or we could say P by T is equal to what? Constant. Okay. Note it down. Okay, clear? Third point. Third point is same way at constant pressure. At constant pressure, volume is proportional to temperature. If we increase the temperature, volume will increase. If we decrease the temperature, volume will decrease. So V by T is equal to what? Constant, or we can say V1 by T1 is equal to V2 by T2. Okay, this is the third law. Okay, so all these three laws, okay, putting together, okay, all these three laws putting together, we got PV is equal to nRT, where P is pressure, V is volume, N is number of moles of given gas. This is gas constant, universal gas constant. Its value is 8.31 mole joule per mole Kelvin. Joule per mole Kelvin, universal gas constant, and this is temperature. Okay, so all those laws putting together, we came to know that PV is equal to nRT, or PV is equal to constant. Okay, that is at a constant temperature, number of, if we get a gas, okay, moles of gas, that will be constant, right? So number of moles into universal gas constant, this is anyway constant. At a constant temperature, PV will be equal to constant. At a constant pressure, V by T will be constant. At a constant volume, P by T will be constant. Okay, clear? So whenever we get a gas, okay, there are two situations, either at a constant volume or at a constant pressure. These two possibilities are there. Okay, so at a constant pressure, what is going to change? Temperature is equal to, again, volume at that particular temperature minus, okay, volume at 0 degree Celsius divided by volume at 100 degree Celsius minus volume at 0 degree Celsius. Okay, so this is the first one, this is the second one. In that itself, we have two types. Next one is thermometric quantity, which is going to change is pressure. Pressure will change. This is at a constant volume. So if this is the case, then you yourself can write the equation. Pressure at that particular temperature, what is the temperature? This is equal to find the temperature, what formula we should use? Pressure at that particular temperature. We will be able to measure the pressure, right, at that particular temperature, minus the pressure at 0 degree Celsius divided by pressure at 100 degree Celsius minus pressure at 0 degree Celsius. Clear? Same structure, only this thermometric quantity will vary. Clear? Fine. Now fourth one, I am erasing this. third one is resistance thermometer. Resistance thermometer. We will be utilizing the variation of resistance, okay, based on temperature in order to find the temperature. Okay, so here the thermometric quantity which is going to change is resistance. Okay, the name of the thermometer is resistance thermometer, and equation which we can use is T is equal to, okay, we are going to find a particular temperature. Okay, some temperature has happened, heat is given, temperature is increased. So when temperature is increased, we need to measure that temperature. So that time the resistance of that wire will change. So what is that resistance? Okay, so that resistance minus the resistance at 0 degree Celsius divided by resistance at 100 degree Celsius minus resistance at 0 degree Celsius, bus over. Okay, so here same formula, but only thing is the thermometric quantity only will change. Okay, note it down. Clear? Okay, so just like how we did for the scale conversion, same way we can do for finding the temperature by taking the thermometric quantity properly. Okay, for some thermometers liquid, okay, volume of the liquid will change. For some thermometers, inside the thermometer there will be gas, so the volume of gas will change. In some thermometers pressure will change, okay, and in some thermometers resistance can change. So based on different applications, okay, we will be using different thermometers based on the necessities. Okay, so here temperature is not constant. Okay, always temperature will be varying. So when when the temperature varies, volume can change, pressure can change, okay, or otherwise resistance can change, or X physical quantity, something. Okay, if they are giving in the question something else, some physical quantity they are giving, then put in the same formula and do it. Okay, so the physical quantity at that particular temperature minus that physical quantity, its value at 0 degree Celsius, divide by this physical quantity at 100 degree Celsius minus this physical quantity at 0 degree Celsius into 100. Okay, into 100 we will have to do. Okay, clear? That's all the formula. Okay, so I am summarizing this. Suppose the temperature, if we need to know, okay, a physical quantity at that temperature minus that physical quantity at 0 degree Celsius divided by the physical quantity at 100 degree Celsius minus that physical quantity at 0 degree Celsius into what? Into 100. Okay, so this is the formula. So here we can put volume, we can put pressure, we can put a resistance, or if we want we can put length or whatever it may be. Okay, certain times how this variation, that is also given in the question, that all things we will practice when we discuss problems. Okay, clear? Okay, fine. Okay, children, so let us discuss problems of this part. Okay, thermometer, and some problems of gas law also in the coming session. Okay, so thank you, goodbye. Hi students, so welcome back to another lecture. So today we are going to see in this session the problems related to thermometers. Okay, already we have seen the basics of thermometry. Now how the thermometer works. Okay, some thermometric physical quantity will be observed and calibration will be done, and based on that we measure the temperature. Okay, so how different thermometers work, okay, and what are their thermometric physical quantities. Some cases may be volume, some cases it could be resistance, sometimes it could be pressure at a constant volume. Likewise, okay, so quickly we will recap those formulae, then that ideal gas equation, then we will move to the problems. Okay, so today in this session, okay, thermometer, okay, so you can say problems on thermometer. Now we will discuss. So first thing is, we have seen ideal gas law, PV is equal to nRT. Okay, and here R, the value of R is 8.31 joule per mole Kelvin. Joule per mole Kelvin. Okay, universal gas constant. P pressure, V volume, N is number of moles, nRT or mu RT, T is the temperature. Then PV is equal to what? Constant. Okay, when we consider temperature as constant, when we make the temperature constant, the product of pressure and volume will be what? Obviously constant. What law is this? This is Boyle's law. Boyle's law. This is found by Robert Boyle. Okay, so under the name Boyle's law. Third one is what? V by T is equal to constant. So this is nothing but at a constant pressure. At a constant pressure, if we vary volume, at a constant pressure, if we vary volume, volume is inversely proportional to temperature. Okay, so this is called Charles law. Charles law. Okay, Charles law. Charles law. Okay, again, another point is also there. Uh, P by T is equal to what? Constant. This is at a constant volume. Constant volume. This is called what? Gay-Lussac's law. Gay-Lussac's law. Okay, so combination of second, third, and fourth law, everything putting together, we can say ideal gas equation or ideal gas law. Okay, PV is equal to nRT. Okay, then for thermometers, so using this law in thermometer based questions also can come. That is why I have mentioned that also. In thermometer, generally what we do, suppose if it is liquid thermometer, if it is liquid thermometer, then the temperature of a particular pressure or volume or length of mercury column, we will have to write like the length that is corresponding to this temperature T minus the length that is 0 degrees Celsius divide by length at length of that column at 100 degrees Celsius minus L0 into 100. This is what liquid. So this can happen in this way also. V minus V naught, that is the volume. It is shown at that particular temperature minus the volume at 0 degrees Celsius divided by V100 minus V naught into 100. This also could be the case. Then gas thermometer. Gas thermometer. T could be what? PT minus P naught divided by, what is PT? The pressure at that particular temperature. How much we are able to get? P pressure at 100 minus pressure at 0 into 100. Okay, this is the case with a constant volume. At a constant volume, this is the case. Another case is what? E is equal to Vt minus V naught divided by V100 minus V naught into 100. This is possible at a constant pressure. Okay, so whenever we deal with the gas, there there are situations at a constant pressure, there are situations at a constant volume also. Okay, one more case we will discuss, that is nothing but a resistance thermometer. In resistance thermometer, let us take extra page. Okay, in resistance thermometer, uh, we have resistance at that particular temperature. So in resistance thermometer, what happens? T is equal to the resistance we are able to measure at that particular temperature minus resistance at 0 divide by resistance at 100 minus resistance at 0 into 100. Okay, so these two cases are there. One more case which I shall tell you, that is nothing but thermocouple. You will come across those questions also when you practice, so that is why I shall tell that also. So thermocouple thermometer, so here the thermometric physical quantity is actually uh, this thermo EMF. Okay, thermo EMF will be generated between the junction of thermocouple. Okay, in detail we don't have to study this. Okay, in detail we don't need to study this. At least this point, these points which I am giving, you just keep it in mind. So here the thermo EMF ET is equal to a constant. Okay, a constant into uh, here it is temperature, actually here it is T, a constant into T plus another constant into T square, where this is thermo EMF. Thermo EMF A and B are constants. So its graph also will be what? Parabolic. Okay, because square term is there. Okay, so thermo EMF. Okay, and the temperature graph is there, that is also will have the shape of parabola. So this also you can remember. Okay, suppose this could be the graph. Okay, in this case EMF and temperature. Okay, so that also you can remember. Okay, now we will move to the questions. Okay, so the first question of this category is the pressure of air in the bulb of a constant volume gas thermometer at 0 degrees Celsius and 100 degrees Celsius are 73 centimeter and 100 centimeter of mercury respectively. So already we have studied the barometer. In barometer, how much is the length of that mercury column? H rho G will be the pressure. So one of the commonly used unit is what? This length of mercury column for calculating pressure. Okay, so we will do. So pressure of air in the bulb. Bulb means that thermometer glass. Okay, in the bulb of a constant volume gas thermometer. This is a volume gas thermometer, constant volume gas thermometer, and the pressure is what varying here. Okay, 0 degree Celsius pressure and 100 degree pressures are given. Now we need to calculate the pressure at 20 degrees Celsius. Okay, so here the temperature at 20 degrees Celsius. This is going to be what? Pressure at 20 degrees Celsius minus pressure at 0 degrees Celsius divided by pressure at 100 degrees Celsius minus pressure at 0 degrees Celsius into 100. This will be the formula that we can expect. Okay, now this pressure at 20 is what we need to find. Okay, let us see. What is the temperature? 20. So 20 is equal to pressure at 20 degrees Celsius minus pressure at 0 degrees Celsius. They have given as length. Okay, let us maintain like that, because the answer also they have asked to calculate the pressure in centimeter of mercury. So 73 centimeter of mercury divided by
pressure at 100 degrees Celsius is given as 100 centimeters. So 100 centimeter of mercury minus again 73 centimeter of mercury into 100. Okay, so if we calculate, we will be getting 20 by 100 into 100 minus 73 will be what? 27. The other side it is minus 73. So this term plus 73 will be what? Pressure at 20 degrees Celsius. Okay, correct or what? So this will be cancelled off. So 2 into 27. Okay, so this will become 1 by 5. So just simplify this, we'll be getting the answer. Okay, so 27 divided by 5 plus 73 is equal to pressure at 20 degree Celsius. With the 5, 27 by 5 will be what? 5 point something. So definitely 73 plus 5 point something will be 78.4. So this will be the answer. So answer is nothing but C. Pressure at 20 degrees Celsius is equal to 78.4 centimeter of mercury. Okay, so this is easy concept, easy problems. Once if you know, we can do. Clear? Shall we move to the next problem? Next problem is the pressure of the gas in constant volume gas thermometer is again 80 centimeter of mercury in melting ice at 1 atmospheric pressure. Okay, so this is constant volume again. So the pressure is given as 80 centimeter of mercury in melting ice at 1 atmospheric pressure. When the bulb is placed in a liquid, the pressure becomes 120 centimeter of mercury. Okay, find the temperature of the liquid in Kelvin. Okay, so here two cases are given. Okay, one case is like the pressure is 80 centimeter of mercury at melting ice and atmospheric pressure is 1 atmosphere. So the bulb is placed in liquid, pressure becomes 160. They are asking the temperature of on the liquid in Kelvin. So here we know this is at a constant volume. Constant volume. So here we need not think like T is equal to P of that particular. Such cases are not given here. They have given two states of a liquid. So easily we can do by using PV is equal to nRT. PV is equal to nRT. So at constant volume, V, N, R, all these are constant. We can write P1 by P2 is equal to what? T1 by T2. So pressure of gas at a constant volume gas thermometer is given as 80 centimeter of mercury. Anyway, that atmospheric pressure will be there. Okay, so it shows 80 centimeter of mercury in melting ice. So 80 centimeter of mercury divided by this P2 is what? 160 centimeter, and a melting ice is at 0 degrees Celsius. So since the answer we need in Kelvin, 273 divided by T2. So okay, what? So T2 is equal to what? 273 into 2. So this is going to be 546 Kelvin. So in between, even without applying that thermometer formulae, okay, we can find the answers. So in this case, that situation is not given, but they have given two states of a liquid is given. One is at melting ice temperature 80 centimeter of mercury, another is at another liquid. The bulb is placed in another liquid. So okay, so I will summarize again. If this is a gas, okay, say for example, if this is a thermometer, okay, if this contains gas. Okay, so this gas has the pressure of 80 centimeter when we kept in melting ice. Okay, suppose if this is melting ice, if we are keeping here inside this, we are getting a pressure here. That is what 80 centimeter of mercury. Now we removed it. Now we have taken another vessel, and this is hotter. So in this we have kept the thermometer. Again, for that one we have got 160 centimeter of mercury. Okay, so that is the comparison. Why they have given that atmospheric pressure? That is one extra detail. We don't have anything to do with it in the question. Okay, means for finding the solution, we need not worry too much about it. But obviously, if the surrounding atmosphere changes, okay, definitely effect can change. That we will see later. Next question. Okay, so in a constant volume gas thermometer, the pressure of the working gas is measured by the difference in the levels of the mercury in the two arms of U-tube connected to the gas at one end. When the bulb is placed at the room temperature 27 degrees Celsius, the mercury column in the arm open to atmosphere stands 5 centimeter above the level of mercury in the other arm. When the bulb is placed in a hot liquid, the difference of mercury level becomes 45 centimeter. Calculate the temperature of the liquid in Kelvin. So here we need not worry. Okay, like a question is lengthy and it is YouTube, then calculating the pressure, then applying the same thing in the thermometer equations. But suppose if you know how YouTube works, and even if you do not know also, they have mentioned, okay, the difference in the level of mercury column is the pressure. And already we have studied all this in fluid mechanics, okay, or mechanical properties of fluids. Okay, just I will show you. Okay, so here this is a thermometer which follows this principle or which is of that nature. So this end is exposed to atmosphere, and here this is we used to connect this to another gas. Okay, we have studied this in uh, mechanical properties of fluids, and this entire thing is called what? uh, Manometer. Okay, so YouTube is connected to manometer. YouTube we study separately, manometer we have studied along with the YouTube. This is also we have studied. Another thing which we have studied is YouTube itself. Okay, YouTube itself. Okay, this also we have studied. So whatever be the case, okay, so this thermometer is made based on this principle. That is the only point. Whatever be the difference of height of mercury column, that is the pressure that they have given very clearly. When the in a constant volume gas thermometer, so this is constant volume, keep it in mind, the pressure of the working gas is measured by the difference in the level of mercury. So pressure means nothing but difference in the level of mercury. That is one point. Okay, what is pressure? Pressure is equal to difference in level. Number two, second point is when the bulb is placed at a room temperature. Bulb means just imagine that it is thermometer. That's it, nothing else. It is placed at room temperature. The mercury column in the open arm to an open arm in the arm open to atmosphere stands at 5 centimeter above the level of mercury in the other arm. That is, the difference in the level here in this case is how much? 5 centimeter of mercury. Another case is when the bulb is placed in hot liquid, that the difference of mercury level becomes, in the second case, the level becomes what? 45 centimeter of mercury. Okay, now what they are asking is calculate the temperature of the liquid in Kelvin. So this one, P1, T1 is given as 27. In P2, T2 is not given. So very simple. Okay, so it's just like applying gas laws, we can solve this problem. Okay, so again, PV is equal to nRT, R, N, V all are constants. So P1 by P2 is equal to T1 by T2. So 5 centimeter of mercury is that level difference. They have given like atmospheric pressure is 75 centimeters. So that also will be there here in with along with the P1. This P naught also we need to consider. P naught or atmospheric pressure is also there. So considering all that, we can write 5 centimeter of mercury plus 75 centimeter of mercury is the total pressure at room temperature. 45 centimeter plus 75 centimeter is the pressure in that hot liquid. This is room temperature given. How much is given? 27 is given. Along with that, I have added 273. Okay, 227 plus 273. I'm getting 300 divided by T2. I do not know which I need to find out. So T2 is equal to what? 80 centimeter by this is going to be 120 centimeter. Okay, T2 is equal to T2 is equal to 300 into 120 centimeter divided by 80 centimeter. So 0 can be cancelled. So this is 2, this is 3. Okay, this is 150. Then that into 3 will become what? 450 Kelvin. Okay, so this is the answer for this question. Okay, option B. Option B is the answer. Clear? Okay. Appear to be little bit lengthy question, but concepts are very simple. Clear? Shall we move to the next problem? Okay, another one. In a same problem, right? Okay, so it came again. Leave it. Next one is this. The resistance of platinum resistant thermometer at the ice point, steam point, and boiling point of sulfur are 2.50, 3.50, and 6.50 ohm respectively. So the resistance of sulfur, okay, resistance of resistance of platinum thermometer at the ice point, steam point, and boiling point of sulfur are given. Now what we need to find the boiling point of sulfur on platinum scale. Ice point and steam point are given. Okay, so boiling point of this we need to find it out. Okay, so there is another thing called the steam point here. Okay, so technically steam point and boiling point have some differences. Okay, so since we don't have that to study, okay, even in thermal properties of matter, we have steam is there, boiling point is there, melting point is there, all that there. But the steam point, okay, since we don't discuss that much, technically what is its difference? We need not know for solving this question. Okay, what we need to know is the general thermometer equation, so that carefully if we substitute the values, the one which we do not know, we will be able to find. Okay, so here in the resistance of platinum thermometer, okay, so ice point, steam point, boiling point, all those resistances are given. Now we need to find what? Find the boiling point of sulfur on platinum scale. Okay, so what is the formula? The temperature is equal to the temperature, the resistance at that particular temperature minus resistance at 0 degrees Celsius divided by resistance at 100 degrees Celsius minus resistance at 0 degrees Celsius into 100. Okay, now let us write here ice point is equal to what? 2.50 resistance. Okay, at ice point. Okay, then steam point. What is steam point? 3.50. Then boiling point. Boiling point is given as 6.50. Now what we need to find, we need to find the boiling point of sulfur. Okay, so this temperature is actually, let us consider that this is boiling point. Now let us put the resistance of boiling point at this place. This is what we need to find. Okay, so 6.50 minus, okay, R naught is nothing but what, resistance at 0 degree Celsius. Resistance at 0 degree Celsius, which is nothing but 2.50, divide by resistance at 100 degree Celsius. We used to do resistance at 100 degree Celsius, we used to find out. Now here in this case, they have given like the ice point and steam point measure at 0 degree Celsius and 100 degree Celsius. So this 100 degree Celsius we can consider as steam point. Okay, the maximum uh, measurement, the maximum fixed point we use to take it as generally boiling point. In this case, they have given like 100 degrees Celsius. So the children, there is something like by varying the pressure or other factors, we can change the melting point and boiling point also. Okay, so some concepts will be there in this question, but what to, in order to solve this, what we need to do is we just need to take that 100 degrees Celsius and 0 degrees Celsius resistances, nothing else. So here R100 is given as how much resistance, steam point is considered as 100. Okay, so 6.50 again minus, sorry, the resistance at steam point is considered as 3.50, that we will substitute. Okay, so 3.50, then again R naught is 2.50 into 100. So T is equal to what? 4 divided by 1 into 100, we will be getting 400 degree Celsius. So this is the answer. Okay, option B. So the boiling point of sulfur in platinum scale is what? How much? 400 degrees Celsius. So here this boiling point is much higher than the steam point. Okay, but no worries. We have considered that 0 and 100 in order to do this. Yes, here upper fixed point generally we have considered as 0 and 100. But in this case, upper fixed point, no, the result is going above the 100 fixed 100 upper fixed point, but we need not worry. In order to solve this problem, this approach can be taken. Okay, so this is another model which we are getting the temperature beyond the upper fixed point also. So using thermometry equation we can find that also. Okay, clear. But 100 degrees Celsius, very clearly they have given us steam point, and ice point they have given as 0 degrees Celsius. So keep those two as upper fixed point and lower fixed point. Now the estimation is nothing but what will be the temperature if the resistance at boiling at steam point is 2.50 and at boiling point it is 6.50 ohm. Okay, is it clear? We'll move to the next problem. Right. Another problem is a platinum resistance thermometer at 0 degrees Celsius and 100 degrees Celsius at the ice point and boiling point of water respectively. Okay, 0 degrees Celsius at ice point, 100 degrees Celsius at a boiling point. The resistance of a platinum wire varies with the Celsius temperature theta as RT is equal to R naught into 1 plus alpha theta plus beta theta square. Okay, so here they have given the function of resistance. This function or this resistance depends on alpha value, beta value, and the temperature also. Okay, and alpha value, beta value both are given. Okay, what will be the reading of this thermometer if it is placed in liquid bath maintained at 50 degrees Celsius? Okay, so what will be the reading of the thermometer? Okay, what will be the reading of the thermometer? So it's generally when we keep thermometer inside 50 degrees Celsius, if the thermometer is accurate, it should give what answer? 50 degrees Celsius itself. Did you understand the question? Every points are given, and what they are saying is this thermometer is kept inside 50 degree. So what will be the reading of the thermometer? It should be 50 degree itself. Okay, but here they haven't given in the option 50, so there will be some differences. Okay, some compromises may be there in the accuracy. So based on those values, it can read in when we even if we put in 50 degrees Celsius also, it can read 45 also maybe. Okay, error will be there. So that could be the situation. If we are getting 50 degrees Celsius, fine, that will be the answer. Okay, so here we will try to find. So this is of JE kind of question. A lot of calculations are there, but we are doing this problem, okay, in order to understand. For JE students, this kind of problems are important. Okay, where calculations are there. For NEET students, in order to understand the concept, this problem is very good. Okay, so let us see. So first point is RT is given as R naught into 1 plus alpha theta plus beta theta square. This is the temperature, this is the resistance of the wire at a temperature T. Let us do, suppose what will be the resistance at 100 degrees Celsius? This is equal to R naught into 1 plus alpha into 50. Okay, so y sorry, not 50, sorry, 100 alpha into 100 alpha into 100 plus beta into 100 square. Suppose if we need to find the resistance of the wire at 50 degrees Celsius, we need to do like R naught into 1 plus beta into 50 plus beta into 50 square. Correct. So this is how we can see the resistances of wire at various temperatures. Now let us find how we can find the temperature of that liquid. T is equal to, it is given as 50, but we will have to find it and verify. T is equal to resistance at 50 degrees Celsius minus resistance at 0 divided by resistance at 100 minus resistance at 0. Okay, so let us see. So temperature T is equal to R naught into 1 plus alpha into 50 plus beta into 50 square. So this is the resistance at 50 degrees Celsius minus the resistance at 0 degrees Celsius divide by resistance at 100. So 1 plus alpha into 100 plus beta into 100 square minus again what? R naught into 100. Clear or what? This formula we have written this one now. Okay, now if we make proper substitution, T is equal to, so if we take this R naught outside, we will be getting 1 plus alpha into 50 plus beta into 50 square minus, okay, so 1, okay, divide by R naught here also we take outside, 1 plus alpha into 100 plus beta into 100 square minus 1, okay, into 100. So r naught will be cancelled off. Another thing is 1 1 1 1 also will be cancelled off. So finally T is equal to what? Alpha into 50 plus beta into 50 square divide by alpha into 100 plus beta into 100 square. Okay, now here in this we will have to substitute, here we will have to substitute the value of alpha. What is the value of alpha? What is given? alpha is equal to 3.8 into 10 raised to minus 3. Alpha is equal to 3.8 into 10 raised to minus 3, and beta is equal to 5.6 into 10 raised to minus 7. That is actually minus. There is negative missing here. Minus. Okay, here one extra equal to. So this is correct. Minus 5.6 into 10 raised to minus 7. So beta is equal to minus 5.6 into 10 raised to minus 7. Uh, uh, okay, minus 5.6 into 10 raised to minus 7 per degree Celsius. Actually, its unit will be per degree Celsius. Okay, it is the units are given as wrong. Per degree Celsius will come. I think so. Yes. So here beta is equal to minus 5.6 into 10 raised to minus 7. So if we make that those substitutions, okay, again we will have to make the 10 raised to values equal, take it outside, cancel them. Then some calculations will be involved, and the answer is going to be 50.4 degrees Celsius. 50.4 degrees Celsius. That is the correct answer for this question. 50.4. Option A should come. Okay, so see this calculation and verify the answer. Okay, so students, here these are the some sample problems on thermometer. Okay, when thermometer comes, the basic formula of thermometer, T is equal to the quantity at that temperature minus the quantity at 0 degrees Celsius. I mean thermometric quantity which is changing based on temperature, divide by that quantity at 100 minus that quantity at 0 degrees Celsius into 100, whether it is resistance, volume, pressure, length of mercury column, whatever it may be. So based on that, we can solve this problem. Okay. Okay, students. So hope you understood. Okay. Thank you so much. Goodbye. We will see in another session.